Okay, let's get started. Um, I've never made a recording before, not without technical assistance, so we'll just give this a try and see how it works. I'm just going to walk through the homework set number 21. This is the homework set that was due, if we can talk about homework being due, yesterday on Wednesday, the 25th of March. There were three problems in chapter 7, 17, 21, and 42. Now this problem 17, that's the bobsled problem, was worked in all its gory detail in that lecture on Wednesday, right at the beginning of that lecture. And so I'm not going to drag you through that again. So let's go right to problem 21 and talk about it. We start with a skier that's coming down a steep slope and then up over a hill. And that skier starts a little bit higher. That skier starts there from rest at point A. And we define this point here to be the lowest point in the problem. We'll call that B, and we'll call this point C. And we're told that she starts 30 meters above what we're calling the floor, and when she gets to point C, she's 25 meters above the floor. We're also told that the mass of the skier is 80 kilograms. Okay. So the first thing we're asked is, what kind of Varick is being done by this frictionless ski hill? And the answer to that is that the Varick done is 0. And it's not that the frictionless ski hill is not pushing, it is pushing. It's just always pushing with a normal force. And that normal force has to act perpendicular to the hill. Well, that's not our best marker. Okay, let's try this one here. Okay, that normal force is always going to point perpendicular to the hill no matter where we are on the hill. And the motion is always going to be along the hill. And since those are perpendicular to each other, the Varick is 0. The normal force is perpendicular to the displacement. Okay. Now part B asks us to find the kinetic energy at point B. Well, one way to go about that is to use the formula for kinetic energy. That's just going to be 1/2 times the mass, which I know is 80 kilograms, times the velocity at B squared. But I don't know how fast she's going at B, so I can't use that formula. What I can use is the grand high energy Varick equation, and that is that the energy in the morning, which in this case would be A, is equal to the energy at evening, which in this case would be later at B, except when it's not, and it's not when there's Varick done in between those two by an external agent. Well, we just said in part A that this Varick is 0. So if I could find the energy at A, that's going to be the same as the energy at B. Well, the energy at A is all potential energy, gravitational, and the energy at B is all kinetic energy. So that tells me that if I just can find out how much potential energy I have here at A, well, that's just the mass times G times the height at A. Well, the mass we're told is 80 kilograms. G is 10 newtons for each kilogram, and the height is 30 meters. And that's going to give me 24,000 joules. Ah, correct. So that means that the energy at B is also going to be 24,000 joules. Well, now you can see that we can work the question we had before, and that is, how fast is it going at B? Turns out that's not one of our questions in the problem, but we could, if we just plugged in the mass as 80 kilograms, we could find out how fast she's going at B and whether she should be wearing a helmet. When she gets to C, we want to know how fast she's going. Well, again, if we use our energy initial is equal to our energy final, except when it's not. And again, we just said that that frictionless hill does no Varick on the skier. So now I just choose what I mean by initial and final. It doesn't matter whether I choose my initial to be here at A or here at B, because I've got the same amount of energy at either of those points. So I'm going to choose it to be at B. I'm looking for information at point C, and so I'm going to make my final event when she gets to point C. So my initial energy is 24,000 joules, and my final energy, I've got two flavors. Because she's moving, I've got kinetic energy, and because she's up off the floor, she has gravitational energy. That's going to be 80 kilograms times G, 10 newtons for each kilogram, times the height of 25 meters. And now I just need to solve for that speed. And at this point, it's just algebra. Folks, I've said this before, I'll say it again. These energy problems very, very quickly just turn into algebra. I mean, we've done the physics, and now it's just solve for x, where in this case, the unknown, the x is the velocity or speed rather at c. And if I solve that, I'm not going to drag you through the details there, but I get 10 meters per second. Now, here's a gut check for you. If you can't work that out to be 10 meters per second, you need to get with someone. You need to get with me. You need to get with your tutorial instructor, maybe the help center. We've got the virtual help center going essentially all day long, every day, Monday through Friday. And you need to get some practice solving these types of algebra problems, okay? Now the next part is asking us for the acceleration of the skier at point C. Well, she's not speeding up and she's not slowing down. I mean, she was slowing down as she went uphill. She's going to be speeding up as she goes downhill. But right here, she's in transition. She's right in between slowing down and speeding up. But she is turning because she's on a curved path. And so whenever you're going on a curve and you're not speeding up and you're not slowing down, you have that centripetal acceleration. And you remember the formula for centripetal acceleration is v squared over r. Well, in this case, let's label that part D. V is 10 meters per second, if you'll believe it, if you can solve that equation there. And the radius here is 25 meters, and that gives me 4 meters per second squared. That's 100 divided by 25. If you had 100 pennies and you divided by 25 pennies, you'd get 4. Okay? And the direction is towards the center of the circle, which is down. Now the last part is a question about force. Part E is asking, what's the normal force on this skier at point C? Well, if I'm asked about a force, what's the first thing I do? What's the first step when I'm solving a force problem? Yeah, free body diagram. Well, that free body diagram for the skier has a weight force, and that's going to be her mass times g. And so that's going to be 800 newtons. There are no magnets in the problem. The only thing touching the skier is the hill, and it pushes with a normal force. And I know that that normal force has to be less than 800 because this diagram has to scream this acceleration down, okay? But how much less? How much should this diagram scream down? Well, the answer to that is always given by F net equals ma, okay? So if I call down the positive y direction and up the negative y direction, then I'm going to have F net, I've got 800 newtons down, I'm calling that positive. I've got my normal force by the hill on the skier, that's up, I'm calling that negative. That's going to equal the mass, which is 80 kilograms times the acceleration of 4 meters per second squared. And it's a positive 4 meters per second squared because it's down, and I'm calling that positive, okay? So that tells me that 800 newtons minus this normal force is equal to 320 newtons. If I solve that for the normal force by the hill on the skier, I get 480 newtons. Talk to your neighbor about that problem. Oh, wait, you don't have a neighbor because you're self-isolating and you're all alone in your room, lonely. Okay, so talk to yourself and try not to be worried that you're talking to yourself. Okay, that's that problem. I'd give you some more time to think about it, but you can always just hit the pause button as well. Let's look at this next problem, 42. I've got a meeting in 15 minutes, so let's get that one behind us. These are both, actually all three of these problems were old exam problems. You come to expect that as we get closer to the midterm. In this case, we've got a launch pad, and then we come down a hill. We've got a rough section of track, and then we go over another hill and to a spring. This would be a spring with spring constant K2, and we're told that this height here is 2 meters. We're told that this rough patch here has a mu sub k of 0.3, and runs for a distance of 1.5 meters. We're told that there's a spring here that has K1 is equal to 64 newtons for each meter. And we start with this spring compressed half a meter. Okay. What else do we know in this problem? Well, we know that when the block gets to, we know that the mass of the block is 3 kilograms. We also know that when the block gets here to what we're calling point C, it's going 4 meters per second. Okay. Now, the first thing we're asked for part A is, what is the Varick done by this friction force here? So the kinetic friction force by the track on the block is how big? No, that's not what it's asking at all. Okay, we want to know, what is the Varick done by the friction? Now, as the block moves this way, the friction force on the block is going to be acting that way. And so we know that the answer to part A, it better be a negative number. Okay, we better get something that's negative. We know the distance is 1.5 meters. So if we knew what this friction force was, the Varick would be given by just minus that friction force by the track on the block times the distance. Well, anytime I'm looking for a force, I draw a free body diagram. I have a weight force that is 30 newtons. If the block is moving to the left and slowing down, the acceleration should be to the right. But none of the acceleration should be up or down here. And so that means the normal force here by the track on the block would also be 30 newtons. The friction force, kinetic friction, is going to be the mu sub k times the normal force. Now, the mu sub k is 0.3, and so that's going to be 0.3 times 30, or 9 newtons. So if I come back here, the Varick is going to be equal to negative 9 newtons times 1.5 meters, and that's going to be negative 13.5, and a Newton meter is just a fancy way of saying a joule. Okay? Now, we want to know just how high this block started out. We'll call that height 0 is the lowest point. Oh, can't do that. Okay. So how high is that block starting out. Now, let's start that over here. Okay. I imagine it's still recording even though my screensaver goes on. So we start with the Grant-Varick energy equation. I pick a time when I need information. That'll be here at point A. And I pick an event where I know all the information, and that'll be here at point C. And then I ask myself, what kinds of Varick did I have at A? And I always ask myself the same three questions. Is anything with mass moving? No. Is anything up off the floor? Yes. So I have gravitational potential at A. The third question is, are any springs stretched or compressed? Yes. So I have spring energy at A. And then I have this Varick that we calculated in part A over there. And then we go to C, and I ask the same three questions. Is anything with mass moving? Yes. So I have kinetic energy at C. Is anything up off the floor? Yes. So I have gravitational energy at C. And the third question is, are any springs stretched or compressed? Not anymore. Okay. So now I plug in what I know. I know that initially I had 3 kilograms, and G is 10 newtons for each kilogram, and the height there is what I'm looking for. And then I had 1/2 times 64 newtons per each meter, that's K, times the delta S, which is 0.5 squared. And then I have to add the Varick, but the Varick is negative, so I'm really subtracting 13.5 joules. And then when I get to C, I've got kinetic energy, 1/2 times the mass times the speed squared. And then I've got this gravitational energy, which is M, 3 kilograms, times G, 10 newtons for each kilogram, times the height there is given as 2 meters. And once again, people, this turns into algebra. This is just plug and chug for the one unknown, which in this case is capital H. And what I get in this case is capital H is equal to 2.98 meters. Okay? Now, again, what I've been using is kinetic energy is 1/2 mv squared, gravitational energy is mgh, and spring energy is 1/2 k delta S squared. And you'll need to have those formulas memorized for the exam. Those will not be given on the exam, as I explained before. Now, this is just like the skier problem. We want to know what is the acceleration of the block at point C. Well, again, it's traveling in a circle, and so the acceleration is going to be centripetal towards the center of the circle. And so if I come over here and do that part D, I'm sorry, I'm part C, don't get ahead of myself. That centripetal acceleration is going to be v squared over r. That's going to be 4 meters per second squared over 2 meters. That's going to be 8 meters per second squared down. Again, we're asked to find the normal force here. Well, if I draw a free body diagram, the weight of the block is going to be 30 newtons. The normal force by the track on the block is going to be less than 30 newtons. Well, how much less? Well, that's given by Newton's second law. If again I call down the positive y direction, then I've got 30 newtons minus the normal force by the track on the block is equal to the mass, 3 kilograms, times the acceleration, which is 8 meters per second squared, and it would be a positive 8 because it's down. When I solve that for the normal force by the track on the block, I get 30 newtons minus 24 newtons equals 6 newtons. Okay. Now I'm running out of time here, folks, so I'm going to race through the last part. By now you should have a clear idea of how to do it. If this spring constant is 42 newtons per meter, and this block comes down from where it is up here and hits the spring and compresses it, how much will it compress the spring before it stops? Well, again, this will now be part E. I use my Varick energy equation. I'm going to take my initial case to be here because I know how much energy there is there. I'm going to take my final point to be where it stops at point D. And there's no Varick in between because the Varick was all over here with that friction. And so the energy, we found that the energy up here was 84 joules. And when it gets down here, that's going to be all in the spring energy, 1/2 K delta S squared. So that means 84 joules is equal to 1/2 times 42 newtons per meter times delta S squared. And now what that gives me is that delta S squared is equal to 4 meters squared, where delta S is equal to 2 meters. Okay, I'm going to get this posted up at the YouTube site, and hopefully it will be helpful to some of you. I wish I could see you, but I understand that I can't. Talk to you later.